Hello, student. Welcome to my YouTube channel, Knowledge Lane, the Physics Classroom. Here you will find the revision of the important topics or the concepts from class 12 physics HSC board. So let's begin. Where we have done in the last video, or we have completed the topic that is vehicle is, or you could say vehicle is driven on a banked road. On a banked road. And we have arrived at the formula with what optimum speed the vehicle can be safely driven on this banked road. But the important point to remember is neglecting friction. Without friction. That means we are assuming kind of thing. The road surface is very, very smooth. So V is equal to R G tan of theta, where R is the radius of curvature, of circular track, though it is banked, circular track. As you know all, G represents acceleration due to gravity. Acceleration due to gravity. And theta is the angle of banking. Angle of banking, yes. Now, with this, if the car or the vehicle, any vehicle is driven on the banked road, in that case, we are neglecting the friction. Then we have seen the different forces which are acting on the car. If I have to show this by diagram, then it will be like this. This is a banked road on which a car is being driven, and here we are not considering the friction between the road surface and the surface of the tires of the vehicle. So here what we have, that the weight of the car is naturally always acts vertically downward. At the same time, this road surface is exerting a normal reaction, and you all know this is perpendicular to the road surface. So the main two forces which are acting on this car when it is driven on this incline or on this banked road is weight mg and the normal reaction exerted by the road surface. So we want to know which force or which component of this normal reaction is balancing the weight and which is providing the necessary centripetal force for the circular motion or for having a turn on this curved banked road. So let us resolve this normal reaction in two components like this. One is along the line of weight mg but in opposite direction. So naturally we know as this is being theta. Using the geometry you can find out this angle will also come out to be theta, and this component, as this is a adjacent side, this is obviously n cos theta, and this which is directed towards the center of that circular banked road represent n sine theta. So for this we have seen n cos theta is the component of the normal reaction which is now balancing the weight of that car, and n sine theta is providing us the necessary centripetal force, which is represented by mv square by r. Yes, and by doing some mathematics over there, over these equations, we have arrived at the final expression for the safest speed with which the car can be safely driven on the curved banked road, but by neglecting friction is v is equal to under root r g tan of theta. Now, it is not always possible to drive a vehicle with this speed, so that sine theta component always provides mv square by r, which is centripetal force, and weight will get balanced by n cos theta component of the normal reaction. We always have in practice that sometimes the vehicle may be get driven with a higher speed than this or the lower speed than this. Then what are the possible safest speed? Either what is the minimum possible speed with which the car or a vehicle can be safely driven on this road so that it won't get slide down on the incline, or what is the maximum speed with which the car or a vehicle can be safely driven so that it is not getting thrown off the road of the incline. So let's have a look on those two important derivation, of which the first one we will be doing what happens if the vehicle is driven with the minimum speed as compared with v equal to under root r g tan theta. The meaning of this is the vehicle is now being driven than the lesser speed of this, whatever, by substituting the values of theta, g and r, whatever the value of that v we will be getting. Now the vehicle is being driven than the lesser speed as compared with this. Okay, so let's draw the necessary figure because that gives you a complete idea. So let's do that. This is the inclined banked road on which a vehicle is now driven with a speed less than the speed represented by this equation, r under root rg tan theta. Okay, so let us complete drawing this diagram. Okay, so this again, this dot, this represent a center of mass of the car, and we know that weight mg will act vertically downward, and the normal reaction exerted by the road surface is perpendicular to the road surface. So these are kind of two obvious forces which are acting on the car, on the vehicle. Now, as we have said that the vehicle is now driven with a minimum speed than the required one. V is equal to under root rg tan theta. This is the optimum speed. So natural tendency is that the car will start sliding down, or the vehicle will start sliding down over the incline. So to avoid that, what happens that a frictional force will come into picture, and this force is naturally directed over the incline in upward direction. So this arrow represents the necessary frictional force that get developed between the road surface and the surface of the tires. If the vehicle is being driven, then the minimum speed, than this v equal to under root rg tan theta. Now let us label these first so you have a complete understanding. This arrow represent normal reaction. This represent weight mg of the car, and now just now we have spoken, this represent the force of friction. Now, as we know, there are two forces, normal reaction and force of reaction. Let us resolve force of friction in two components, like one is upward over the incline and one in normal vertically upward direction, which obviously as in the same direction as that of the n cos theta component of the normal reaction. Simultaneously, what we have seen, that normal reaction, if we resolve, then this component represent n sine theta. So let us label all these factors. If this is the angle of banking, quite obvious, this is also theta. And we have seen by using the geometry, this angle comes out to be theta again. So in case of this normal reaction, this arrow will represent n cos theta. This will be representing fs sine theta. Obviously, this one is fs cos theta. And the remaining one, this arrow is directed towards the center along the radius of the track. So this is being n sine theta. Okay. Now we know from the figure that now weight mg is getting balanced by two vertically upward directed forces, n cos theta and fs sine theta. So we have our first equation here. Mg is equal to n cos theta, as both the forces are acting in the same direction. So addition sign is there, n cos theta plus fs sine theta. And here mv square by r, which is the necessary required centripetal force for taking a turn on that inclined banked road, which is mv square by r. Now it is being balanced by these two forces, n sine theta and fs cos theta, but as they are oppositely directed, naturally we have to put a minus sign over there, fs cos theta. Now we want to solve these two equations for v. We want to find out the expression for v, the minimum speed with which the vehicle being driven on this banked inclined road or banked road without getting slide down that incline. So for this, what we do, let us label these equations. Say this is equation 1 and this is as equation 2. Dividing equation 2 by equation 1. What we get is this. mv square by r get divided by mg, which now is equal to n sine theta, minus fs cos theta upon n cos theta plus fs sine theta. So as we see from the left hand side of the equation, m will get cancelled and we have b square by rg on the LHS side of this equation, which is equal to now n sine theta minus fs cos theta upon n cos theta plus fs sine theta. Okay. As we know, this force of friction is equal to mu Sn, where mu s represent coefficient of friction, and n is a normal reaction. So let's call this as equation 3, and we write substituting Fs equal to mu Sn in this equation 3. So let's do that. Substituting this in equation 3. What you get is like V square by Rg equal to n sine theta minus, now we write in place of Fs as mu Sn cos theta divided by n cos theta plus mu Sn sine theta. Okay. Here on RHS, what we see, n is common in all the terms, so we can easily cancel it out. N get cut, so it remains only sine theta minus mu s cos theta divided by cos theta plus mu s sine theta. Now what we do is dividing numerator and denominator. Numerator and denominator. On RHS of above equation by cos of theta. We get C. Here we'll get V square by Rg equal to sine theta by cos theta minus mu s cos theta by cos theta. We are dividing each term on numerator and denominator by cos theta. So this will look like cos theta by cos theta in the denominator plus mu s sine theta by cos theta. And you know sine by cos represents tan. So the expression becomes V square by Rg is equal to tan of theta for this term minus, here cos theta cancel out, so you have mu s only divided by cos theta is giving you 1 plus again sine theta by cos theta becomes tan of theta. So in the denominator we have 1 plus mu s tan theta. Yes. And now here I am opening the new page. V square by Rg is what it gives us, tan theta minus mu s upon 1 plus mu s tan theta. As we are interested in finding out the value of V, let us rearrange this for V square first. So it is like Rg times tan theta minus mu s upon 1 plus mu s tan theta. So taking the square root on both sides, we will have V is equal to, which is our required expression or for which we are deriving this, under root Rg tan theta minus mu s upon 1 plus mu s tan of theta. That's it. So this is a required expression if the vehicle being driven with a speed less than minimum optimum speed, which is represented by V is equal to under root Rg tan theta. Okay, so this is what we got, and this is nothing but, let us write that this expression gives minimum speed with which vehicle can be safely driven on a banked road without skidding downwards. Yes. So this is one of the important expression, important derivation you can say. Many times it is asked in the board exam. Now we will see the second type of derivation similar to this, but now in this case, the second case, we are considering the vehicle is driven with a higher speed than the required optimum speed. V is equal to under root R G tan theta. So this is the optimum speed which is required so as to avoid the being thrown off. But still, in some cases, if the vehicle is being driven than the greater speed represented by this equation, then what should be the maximum safest speed? Maximum safest, safest speed for a vehicle being driven with higher speed than V equal to under root Rg tan theta, which we call it as a maximum optimum speed. Okay, so to understand this, what should be the maximum speed that vehicle should take so as to it is not being thrown off that banked road? So let us draw the required figure as it's a important part for getting good score in the theory exam. Obviously, all this what we are seeing is for scoring good marks. Is now this is the inclined banked road. Now the car or a vehicle is now being driven on this incline, and what we have assumed, now it is driven with a higher speed than V equal to under root Rg tan theta. Naturally, we have to explain the different kinds of forces acting on that vehicle if it is driven with that speed. So let us show it diagrammatically first. As we know, mg, the weight of the car, the weight of the vehicle always act vertically downward. N being the normal reaction exerted by the road surface on the car. Now first, let us resolve this normal reaction in two components. As we know, one is along mg but in opposite direction to mg, and other is towards a center of the circular track and along the radius. So these two components represent n cos theta and n sin theta. And what is theta? Theta is angle of banking. By doing geometry, we will know this angle also being theta. Now, when this vehicle is getting driven with a higher speed than v equal to under root rg tan theta, there is a possibility that it will get thrown off the road. So to avoid that slipping outwards or being thrown off the road outwards, the force of friction plays an important role. And this force of friction is now act just to avoid being thrown off in outward direction. It will act inwards like this. So this is the force of friction. Now, in this case, as it is inwards, we will resolve this in two components like this. So let us label this. This is force of friction. Now, if this angle is theta, then this is an alternate angle. So this is being theta. So what it gives you, this component is now Fs cos theta. And this component is Fs sin theta. What does this arrow represent? It represents weight of the car acting vertically downward. So seeing this diagram, what two equations we have is mg, the weight, is now getting balanced by n cos theta and fs sin theta, but both these forces are oppositely directed. So we'll have to write the equation as n cos theta minus fs sin theta. This is equation 1. And the second one, n sin theta. Now along with this, in addition, we are having a component called as fs cos theta. Both of these are along the radius and towards the center. So combinedly, these two forces are acting or providing us or to the car the necessary centripetal force. So let us write mv square by r is n sin theta plus fs cos theta. This is our equation 2. As per the previous derivation, here also we'll do dividing equation 2 by equation 1. Since we want to find out the expression for v. What we get, let us write that mv square by r upon mg is equal to n sin theta plus fs cos theta divided by n cos theta minus fs sin theta. Okay, here as we see, m will get cut and what we have is v square by rg equal to, it remains now n sin theta plus fs cos theta upon n cos theta minus fs sine theta. So Fs is the force of friction between the surface of the road and the surface of tires. So it is represented by mu Sn, where mu S is equal to coefficient of friction and N is equal to normal reaction. So substituting this Fs equal to mu S N in this equation 3. What we get? Let us write down. Substituting Fs equal to mu S N in equation 3. We get V square by Rg is equal to N sine theta plus mu Sn cos theta divided by N cos theta minus mu Sn sine theta. So as we see, numerator and denominator, every term on RHS has N, so it can be easily cancelled out, and we get the remaining terms as V square by Rg is equal to sine theta plus cos theta upon cos theta minus mu s, mu s sine theta. So what it remains now, the trick that you have to remember, dividing numerator and denominator on RHS of above equation by cos theta. Okay, here also I have forgotten mu s, so let's write that mu s cos theta, yes. So dividing numerator and denominator on RHS of above equation by cos theta, we get V square by Rg is equal to, let us show that, sine theta by cos theta plus mu s as it is, cos theta by cos theta, divided by, in the denominator we have cos theta by cos theta minus mu s time sine theta by cos theta. Again, sine by cos represents tangent ratio. So we get V square by Rg is equal to tan of theta plus mu s divided by 1 minus mu s tan theta. Again, rearrange the equation for V square. Here, I am opening the new page. So rearranging this, V square is equal to Rg times tan theta plus mu s upon 1 minus mu s tan theta. Therefore, taking square root on both sides. Taking square root on both sides. On both sides, we get V is equal to under root Rg times tan theta plus mu s upon 1 minus mu s tan of theta. Yes, this is the required expression if the vehicle being driven with a higher speed than the minimum optimum speed, which is nothing but v equal to under root rg tan theta. So let's write that statement. This expression gives this expression gives the maximum safe speed with which a vehicle can be safely driven on a banked road, but the speed here is greater than v equal to under root rg tan theta. Okay, understood? So this is it. These two derivations are of much importance because they are many times repeatedly asked in your board class 12 board exam. If you want to have such revision of different topics from class 12 physics theory book textbook for a board theory exam, stay tuned with my YouTube channel Knowledge Lane the Physics Classroom. See you in the next video. Thank you.